Welcome. Today we'll take a look at graphical models, specifically Bayesian networks or Bayes nets, as well as a method for performing inference with these models called expectation maximization. So let's start by looking at this story. We'll consider the following four indicator random variables for an individual: the indicator of the event that they're a smoker, the indicator of the event that they exercise regularly, the indicator of the event that they possess a particular gene which predisposes them to lung cancer, and the indicator of the event that they contract lung cancer. And we would guess that the joint distribution on these four random variables is relatively complex. They're presumably not independent, and it would be nice to have a way to describe their dependency relationship somehow. And this story provides one such way. It tells us how to sample from this joint distribution. It says, begin by choosing smoker or non-smoker with probabilities 18% and 82%. Then, with that random choice in hand, we choose exercise or non-exercise with probabilities that are specified here depending on that initial choice. Then for the gene, we can make that choice without referring to any of the previous choices. And here for the very last choice, we have to look at all of the choices above. Part A asks us to translate this story into a diagram in which each indicator random variable is a node. And we're going to draw arrows indicating when we had to account for previous events when we sampled each random variable moving forward through the story. So we started with the smokes random variable, and then we had to account for that when we selected the exercise random variable. Then we sampled the gene random variable independently of the other two. And finally, the conditional probability of the lung cancer random variable is specified in a way that depends on all of the other three random variables. So again, this diagram is called a Bayes net or Bayesian network. And again, it's a description of how a collection of random variables are related in the context of a particular sampling algorithm, where the conditional distribution of each random variable is specified in terms of previous ones. In part B, we're asked, is this the only such diagram that we could use to sample from this same joint distribution? If you think about it, what's going on between the smoking and exercising random variables is that they have some joint distribution that we happened to sample by first selecting smokes from its marginal distribution and then selecting exercises from its conditional distribution given smokes. But we could just as easily have proceeded in the opposite direction. So Bayes net is specified not by the actual joint distribution, but by a specific algorithm for sampling from that distribution, which proceeds one random variable at a time. And the kind of things we can deduce from a Bayes net are observations like smoking and having the gene are independent, because in the process of following this Bayes net to sample from this joint distribution on these four random variables, we did sample the gene random variable already knowing the value of the smokes random variable, and its conditional distribution did not depend on the value of the smokes random variable. On the other hand, the lack of a connecting arrow doesn't imply independence in general. For example, if we consider adding a fifth random variable to this network, which indicates whether a person gets premature wrinkles, then that random variable will not be independent of the smokes random variable. Its conditional distribution given the smokes random variable will depend on the value of that random variable. And as you might guess, the lack of a direct connection between the wrinkles and the lung cancer random variables doesn't imply that they're independent, but it does imply that all of their dependence can be explained by this intermediate smokes variable. So notice that the Bayes net diagram doesn't actually specify the probability measure because it doesn't communicate what the conditional probability measures are for each random variable given its parents in this diagram. That we need to write down separately as we did in problem 1 in the paragraph description of this measure. Part C asks us to find the marginal distribution of the exercise random variable. So notice that the way the distribution of this random variable is specified, its marginal distribution is not obvious. What we get is its conditional distribution given the smoking random variable. However, we can say the probability that the individual exercises is equal to the probability that they're a smoker times the probability that they exercise conditioned on the event that they're a smoker, plus the probability that they're a non-smoker times the probability that they exercise conditioned on the event that they're a non-smoker. And since the exercise random variable is an indicator, the probability that it's true or equal to 1 fully specifies the measure. So this is the probability that it's 1, and 1 minus this value is the probability that it's 0. And more generally in a Bayes net, we can start at the root nodes, the ones which have no parents, and work downwards through the diagram to come up with marginal distributions for each of the other random variables. So in problem 2, we're asked to come up with our own Bayesian network with the property that one of the random variables has a particular distribution, specifically a mixture of Gaussians. So this is a density that can be expressed as a linear combination of two multivariate normal densities where the weights are non-negative and add up to 1. So a linear combination with weights non-negative and adding to 1 is called a convex combination. So we can say that a mixture of Gaussians is a distribution which can be written as a convex combination of multivariate Gaussian density. So here's one example where the two humps coming from the two densities are fairly separated so that you can tell them apart quite well. But it can also be the case that the means are closer together relative to the covariances, and these two humps end up blurring together. So the prompt is to come up with a Bayes net that involves a random vector that has this distribution. So we could certainly do that in a very cheap way by just having a one-node Bayes net and specifying this as its density. But to avoid trivializing the problem, what we want to do is think about how we would actually sample from this distribution. And think about the hidden randomness that's used inside that algorithm. So what we could do to achieve that convex combination is sample a Bernoulli with probability 0.55, since that's the proportion for this first density function. So you can see that this scatter plot does match up with this density. In any case, this function is showing us what the extra random variable should be in our Bayes net. It should be this Bernoulli with probability 0.55. So we're going to call that random variable z, and we're looking at its value to compute x. So z is going to be a Bernoulli random variable with success probability 0.55. And the conditional distribution of x given z is a multivariate normal distribution whose mean depends on the value of z and whose covariance depends on the value of z. So this is just another way of saying that if z is 0, then x should be drawn from a multivariate normal with mean mu 0 and covariance sigma 0, and if z equals 1, then x should be drawn from a multivariate normal distribution with mean mu 1 and covariance sigma 1. So this is a very simple Bayes net diagram, but it's already going to offer a significant amount of inference challenge. So the goal is going to be to take observations at the end here and draw conclusions about all the parameters of the model. So that will include mu 0 and mu 1, as well as sigma 0 and sigma 1, as well as the success probability for this Bernoulli random variable. So we'll call the Bernoulli parameter alpha, and we'll combine all of these parameters we want to estimate into a single quantity called theta. So to get a visual sense of what we're trying to do, let's look at a new pair of multivariate normal distributions and a new value of alpha and make a scatter plot. So these blur together a bit more than the ones above, but still your visual cortex doesn't have too difficult a time teasing out which are the two clumps. If you were going to fit a mixture of Gaussians by hand, you would probably decide pretty quickly that you want to fit one of the two multivariate normal distributions to this clump at the top, and you want to fit the other one to the remaining points down here. But from the machine's point of view, it doesn't see these two clusters. All the points here are gray, and it has to do its own job of coloring them. We're going to use orange and blue. So it has to decide these points should be orange and these points should be blue. So we'll start thinking about how to do that. And one concept when you don't know what to do is just start somewhere and see what happens. So we could just throw down two multivariate normal distributions somewhere, like center 1 at 3, 3 and 1 at 1, 6. And let's just use the identity matrix for both covariances. So visually we have this blue distribution and this orange distribution. Our next move is going to be to take these blue and orange distributions and use them to judge the points and decide whether they're more blue or orange. In other words, for each point, we're going to assess its conditional probability of having come from z equals 0, which corresponds to blue, or z equals 1, which corresponds to orange, bearing in mind that we don't get to observe the value of this hidden variable z. So this is really very similar to a classification problem in some ways, except that we never get to see any labels. So we don't get to train on labels, and we're not trying to predict labels. We're just trying to fit a density to these data. So the hidden variables will only ever be implicit, in contrast to a supervised classification problem where in the training set you do have these 0 or 1 values for each point. So one really simple thing to do here is just draw a line through the middle, which separates the region which is closer to the orange center from the region which is closest to the blue center. Call everything on this side blue and everything above orange, and then fit this orange distribution to the orange points and the blue distribution to the blue points. And in fact, what we're going to do is very similar to that, but we want to do it in a little smoother way. Rather than taking every point and treating it as strictly blue or strictly orange, we'll treat every point on a sliding scale between 0 and 1, where the value associated with that point is just going to be its conditional probability of being blue when we look at the blue distribution, or being orange if we look at the orange distribution. So we just need to compute for each point, based on our current means and covariances for the two distributions, what's its conditional probability of being blue and what's its conditional probability of being orange. So we already solved this problem when we talked about classification. What we want to do is look at the amount of density sitting at the point x1, x2 coming from the orange distribution, as well as the amount coming from the blue distribution, and then we just compute the proportion. So this is orange plus blue in the denominator, and this is just orange in the numerator. So orange over orange plus blue gives the conditional probability of being orange given the location of the point x1, x2. So as you might expect based on this figure, the vast majority of the points are significantly closer to 1 than the other, and are going to come out in this calculation as very strongly blue or orange. So we get lots of values quite close to 0 and lots of values quite close to 1, and not so many in between. So we see this one 0.46, this one 0.16, so those are probably values quite close to this line that's a perpendicular bisector of the segment connecting the two centers. And to visualize this better, what we're going to do is supply a mixture plot with this extra information of how it should color the points. So we end up with some points really quite orange. These are the points whose values are really close to 1 in the vector pi, and other values that are quite blue. Then in between you can see some that are part orange and part blue. These ones in the middle have pi values closer to the middle of the interval. So now we're going to do the thing we decided to do previously, which is to fit this blue distribution to these blue points, but really to all the points, but just in such a way that each point gets credit in proportion to its blueness. So these orange points will get scores very close to 0 for purposes of calculating the new mean and covariance here, and the blue ones will count almost full credit since they're very close to 1. And likewise, we'll flip all of those scores to compute the orange mean and covariance, and that's going to do a much nicer job of fitting this collection of points up at the top. So our new alpha value, which we also have to update, is just going to be the total orange score. So we sum all the pi's and divide by n. That's the proportion of points which are orange, where instead of counting every point strictly orange or blue, we give it an orangeness score between 0 and 1, and then perform a weighted count. So next we want to compute our blue mean, mu0, and remember that pi stores the orangeness scores. So we need to do 1 minus that to get our blueness scores. So do 1 minus pi, and then we want to multiply each of those blueness values by the corresponding entry of the vector x1. So that's a dot product. And then same idea for the second coordinate. And then this is a weighted average, so we have to divide by the sum of the weights. So that's the sum of all the blueness scores. Same idea for orange, but we don't have to subtract from 1. And then really we can do the same thing for the sigmas, with the caveat that round-off errors end up causing the off-diagonal entries to be slightly unequal. And then the distributions package complains if you give a non-symmetric matrix as your covariance matrix for your multivariate normal distribution. So we can solve that by calling Hermitian on the resulting matrix. So here's our weight, 1 minus pi, and we're doing x times x transpose, as we usually do when we compute covariances. And then we're using this weighted average instead of a straight average. So we have to divide by the sum of the weights as well. And again, we call Hermitian and then convert it to an ordinary matrix so that the distributions package won't fuss. And then we can visualize this new updated set of parameters. And as suspected, it did a much nicer job than the original choice. However, it's still not great. This orange one is leaning down more than it probably needs to because these points counted as fairly orange in that original guess. And likewise, we can imagine this blue one can use a little bit of adjustment as well. Really what's going on is that we started with a guess that wasn't very good, and then we computed our pi values, our conditional probabilities of coming from one distribution or the other, in terms of that initial bad guess. So we really should update that as well. And with that updated, we can recolor the points. So most of the points didn't change that much because they were already either very blue or very orange, but the ones in the middle did. And now if we do this whole thing again, these distributions will have an opportunity to fit the points that belong to them even better. So let's do it. What we find is that this one gets flatter and tightens up a little bit, as does this one. And why not do it one more time, even a few more times? However, we start to see that it's really stabilized. It's converged to a point where the alpha, mu, and sigma updates don't really affect the pi values, and conversely, the pi values don't really cause the alpha, mu, and sigma values to update either. So this is called the expectation-maximization algorithm, and we've presented it here in the context of this specific example so that we can have a firm example in mind when we discuss the more general version next time. So in summary, a graphical model is a visualization of dependency relationships among random variables. A BayesNet or Bayesian network is a specific example of a graphical model that represents dependency relationships using a directed graph. And specifically, the dependency relationships are the ones described in a particular algorithm for sampling from the joint distribution on the collection of random variables. For example, with this BayesNet, we could sample x1, then sample x4 from its conditional distribution given x1, then sample x2 independently of those, and then sample x3 from its conditional distribution given x1 and x2, and so on. A Gaussian mixture model is a distribution whose density is a convex combination of multivariate normal densities. Finally, expectation maximization is an inference algorithm, so an algorithm for coming up with parameter values that align well with observed data, that involves alternating between optimizing the model parameters and then recomputing the conditional distribution of the unobserved random variables given those parameters. And we looked at that specifically in the context of Gaussian mixture models, where we started with some guess for the multivariate normal distributions, and then for each point identified its conditional probability of having z equals 0 or z equals 1, and then refit the model parameters based on those conditional probabilities. At this point, we can recompute the conditional probabilities, adjust the model parameters again, and so on until convergence.